Welcome back to DevOps Basics with Dolly. In this episode, we're going to learn about Terraform Data Sources. Until now, we've mainly used Terraform to create new infrastructure, but in real-world projects, not everything needs to be created from scratch. Many AWS resources may already exist, such as VPCs, subnets, security groups, or machine images. Data sources allow Terraform to read information about those existing resources and use them in our configuration. By the end of this episode, we'll deploy a new EC2 instance using AWS infrastructure that already exists. Here's what we'll cover in this episode. We'll start by understanding what Terraform data sources are and why they're useful. Then, we'll go to the official Terraform documentation and learn how to find and understand a data source before writing any code. After that, we'll create our first AWS_AMI data source and use it to replace a hard-coded AMI ID in our Terraform configuration. Once that's done, we'll update our EC2 resource to use the value returned by the data source instead of a manually provided variable. Then we'll validate our configuration, generate an execution plan, and deploy the infrastructure. After the deployment, we'll verify the results both in the AWS Management Console and from Terraform itself. Finally, I'll show you how I use AI to identify other opportunities to replace hard-coded values with Terraform data sources in real-world projects. By the end of this episode, you'll understand not only how to use data sources, but also how to recognize when they're the right solution for your infrastructure. As always, we'll start with the official documentation. First, we'll find the data source we need in the Terraform AWS provider documentation. Then, we'll understand what information it reads, which arguments it accepts, and which attributes it returns. After that, we'll implement it in our Terraform project, validate the configuration, and test the result. We may use AI if we need additional clarification, but the official documentation will remain our source of truth. This is the workflow we want to follow as DevOps engineers. Documentation first, understand the feature, implement it, validate it, and then deploy. For example, this is the documentation for the AWS_AMI data source. It allows Terraform to search for an existing AMI and return its ID. Terraform doesn't create the AMI. It only reads information about an AMI that already exists. Before we start working with data sources, let's talk about our project structure. Instead of creating a brand new Terraform project, we'll continue using the project from the previous episode. This is much closer to how Terraform is used in real-world environments. Infrastructure projects evolve over time. We don't recreate everything from scratch every time we need a new feature. Instead, we improve the existing configuration by adding new resources, new modules, or in today's case, data sources. We already have a working Terraform project. Our provider is configured. We have input variables, we have outputs, and we already know how to deploy an EC2 instance. Today, we'll expand this project by teaching Terraform how to discover existing AWS resources instead of hard-coding their IDs. In the previous episode, we stored values inside our dev.tf_vars file. Today, we'll discover that some values don't need to be stored manually anymore. Terraform can retrieve them directly from AWS using data sources. Before writing any code, let's understand the concept from the official Terraform documentation. Terraform uses data sources to read information from an external system. In our case, that external system is AWS. A data source can retrieve information such as an AMI ID, a VPC ID, subnet IDs, or the name of an availability zone. Let's take a closer look at this example. This is the official example provided by the Terraform AWS provider documentation for the AWS_AMI data source. At first glance, it may look a little overwhelming, but don't worry. We don't need to understand every line immediately. Instead, let's identify the main parts of the configuration. Notice that the block starts with the data keyword. That tells Terraform we're reading information from AWS instead of creating a new resource. Next, we have AWS_AMI, which is the type of data source we're using. And finally, Example is simply the local name Terraform will use to reference this data source inside our configuration. Everything inside the block defines how Terraform should search for the AMI. Some arguments narrow down the search, while others define which result Terraform should return. We'll understand each of these arguments as we adapt this example to our own project. Now that we understand the overall structure, let's bring this example into our project. I'm going to copy it exactly as it appears in the official documentation. Then we'll go through it line by line and modify it to match our AWS environment. This is exactly how you'll work in real projects. You start from the official documentation, copy a working example, and then adapt it to your own requirements. Let's start with the data source name. AWS_AMI is the data source type, so we won't change it. However, example is only a local name used by the documentation. We want a name that clearly describes what this data source will return. Since we're searching for an Amazon Linux image, we'll rename it to Amazon_Linux. Later, we'll reference it using data.aws_ami.amazon_Linux. Next, we have executable_users set to self. This restricts the search to images that our current AWS account can execute under that specific condition. We don't need this argument for our example because we'll identify the image using its owner and a set of filters. So let's remove it and keep our search configuration focused on what we actually need. We'll keep most_recent set to true. Amazon publishes new versions of Amazon Linux regularly, so our filters may match more than one AMI. With this option enabled, Terraform selects the newest image that matches our search criteria. This allows us to avoid hardcoding an AMI ID that may become outdated. The documentation also uses a regular expression called name_regex. It's searching for a custom naming pattern that begins with Miami, followed by 3 numbers. That pattern belongs to the documentation example and doesn't represent the Amazon Linux images we're looking for. We could replace this regular expression, but to keep the example beginner friendly, we'll remove it and use the name filter below instead. Now let's look at owners. In the original example, self means the AMI must be owned by our current AWS account, but we aren't searching for an AMI that we created. We want an official image published by Amazon, so we'll change the owner from self to Amazon. Restricting the owner is important because it prevents our search from selecting an unrelated image published by another account. This first filter searches by the AMI name. The documentation searches for names beginning with Miami, but those images don't exist in our project. We'll replace that pattern with the naming convention used by standard Amazon Linux 2023 images. The asterisk is a wildcard, so the version and release information can change while the image still matches our search. We are also choosing the x86_64 architecture because it is compatible with the EC2 instance. We'll keep the root device type filter. Setting it to EBS means we only want AM is whose root volume is backed by Amazon EBS. This further narrows the search and makes our selection more specific. We'll also keep the virtualization type set to HVM. HVM is the virtualization type used by modern EC2 instance families. Again, this filter helps ensure Terraform returns an image compatible with the instance we plan to deploy. Finally, let's add one more filter for the architecture. We'll explicitly request x86_64. Even though the architecture is already included in our name pattern, adding this filter makes the requirement clear and makes our search more precise. Now our data source is ready. We started with the official documentation example, understood its structure, and adapted it to our actual requirement. Terraform will now ask AWS for the most recent official Amazon Linux 2023 AMI that matches these filters. Notice that we still haven't created anything. This block only describes the information Terraform needs to read from AWS. Next, we'll add an output so we can verify which AMI Terraform discovers. We'll create a simple output that displays the ID of the Amazon Linux AMI found by our data source. This is a great way to confirm that our configuration is working before we start using that value in other resources. Before running Terraform, let's format and validate our configuration. Everything looks good, our configuration is valid, and Terraform is ready to work with it. Before we continue, we need to make one more update to our project. In the previous episode, we stored the AMI ID inside our dev.tf-vars file and declared it as an input variable in variables.tf. That made sense because Terraform expected us to provide the AMI ID manually, but that's no longer the case. We now have a data source that automatically discovers the latest Amazon Linux AMI directly from AWS. Since the AMI is no longer an input provided by the user, we don't need the AMI_ID variable anymore. First, let's remove it from our dev.tf-vars file. And now let's remove the variable declaration from variables.tf as well. Finally, let's update our EC2 resource. Instead of using var.ami_id, we'll reference the value returned by our data source. This is one of the biggest advantages of data sources. Instead of hardcoding an AMI ID or asking the user to provide one, Terraform can retrieve the correct value directly from AWS. Our configuration is now cleaner, easier to maintain, and much more dynamic. Oops, I forgot to configure my AWS credentials. Let me quickly recreate them, and then we'll run Terraform plan again. Perfect. Terraform successfully read the latest Amazon Linux AMI from AWS. We can see the AMI ID here, AMI-00061186002 DFC1C09. Terraform then used that value to create our EC2 instance. Notice that the AMI itself was not created by Terraform. It was only discovered through the data source and referenced by our EC2 resource. Our existing project also created the security group and its inbound and outbound rules. So the final result was 4 new Terraform managed resources. The output confirms that our data source is working correctly, and we no longer need to hardcode or manually provide the AMI ID. The execution plan looks exactly as expected. Terraform found the AMI, and now it's ready to create our EC2 instance using that existing image. Let's apply the configuration. Perfect. Terraform has successfully created our EC2 instance. More importantly, it automatically discovered the correct Amazon Linux AMI without us having to provide an AMI ID manually. That's the power of data sources. They allow Terraform to consume existing infrastructure and use it as part of our configuration, making our code cleaner, more flexible, and easier to maintain. Let's go back to the terminal. We also created an output that displays the AMI ID returned by our data source. As you can see, the output matches the AMI used by our EC2 instance. This confirms that our data source worked exactly as expected. Now that we've learned how to replace a hard-coded AMI with a data source, let's take one more look at our dev.tf-vars file. A good DevOps engineer is always looking for opportunities to reduce hard-coded values. Looking at this file, what other values could potentially be replaced with data sources? Instead of guessing, let's ask AI. Looking at this Terraform project, which variables could be replaced with Terraform data sources? Explain why and give me the appropriate data source. Before we continue, I want to mention something very important. In this course, I'm showing my AWS access key and secret access key only for educational purposes. Never share your AWS credentials with anyone, and never publish them in your code, Git repositories, screenshots, or videos. As a best practice, if you accidentally expose your credentials, revoke them immediately, and create a new access key. The response is very interesting. According to AI, there are two strong candidates. The first one is our VPC ID. Since a VPC already exists in AWS, we don't have to hardcode its ID. We can discover it dynamically using the AWS_VPC data source. In fact, we've already done that in this project, so this value is no longer needed in our .tf vars file. The second recommendation is our security group CIDR. Instead of storing the VPC CIDR as another variable, Terraform can read it directly from the VPC data source. That means we avoid duplicating the same information in multiple places. AI also explains that the remaining values should stay as variables. Things like the instance type, environment, project name, resource names, and tags are deployment decisions. They're not existing AWS resources, so data sources are not the right tool for them. AI gives suggestions, but it's our job to validate whether they still apply to the current project. Due to time, we won't implement all of these suggestions today. I'll update the project after this video and upload the changes to the GitHub repository. That way, we'll start the next episode with a cleaner and better structured Terraform project with the appropriate data sources already in place. Feel free to compare the code and explore the changes before moving on to the next lesson. Before we finish, let's clean up everything we created in this demo. One of the biggest advantages of infrastructure as code is that creating resources is easy, but cleaning them up is just as easy. This helps us avoid unnecessary AWS charges and keeps our environment clean. Perfect. All the resources managed by Terraform have now been removed successfully. Our AWS environment is back to the same state it was before we started this demo. There's one more thing I'd like to do before we finish. For this demo, I created a temporary IAM user with programmatic access. Since we no longer need those credentials, it's a good security practice to remove them. Never leave temporary credentials active if you're not going to use them. Let's quickly recap what we accomplished today. We learned what Terraform data sources are and why they're useful. We explored the official Terraform documentation and adapted the official example to fit our project. We created our first AWS_AMI data source and used it to automatically discover the latest Amazon Linux AMI. We replaced a hard-coded value with a dynamic reference, making our Terraform configuration cleaner and easier to maintain. We validated our configuration, deployed our infrastructure, and verified the results both in Terraform and in the AWS Management Console. Finally, we saw how AI can help us identify other opportunities to use data sources without replacing the official documentation. Remember the workflow we've been following throughout this series: official documentation, understand the feature, use AI to accelerate your work, validate the results, then deploy with confidence. In the next episode, we'll learn how to use Terraform expressions and functions to write cleaner, smarter, and more dynamic configurations. Thanks for watching, and I'll see you in the next video.